Hola a todos, ¿qué tal? Bienvenidos de nuevo al seminario de álgebra de la Universidad de Guadalajara. El día de hoy, we have an invited speaker. It's Barbora Hudcová, and she will talk to us about the simulation limitations of affine cellular automata. What are cellular automata able to compute? Thank you very much, Barbora. We are looking forward to hear your talk. Thank you.
Okay, so welcome everyone. I just wanted to say that this talk will be more technical than talks I usually give, but I had to take the opportunity of having an algebraic audience, which makes me very happy, or an audience with an algebraic background. And if you have any questions regarding you not understanding the way I explain something or anything else, just let me know right away. I'd be happy to answer. And yeah, so I'm currently a postdoc at EPFL in Lausanne, Switzerland, working on topics related to complex dynamical systems and artificial life. And before that, I did a PhD in Prague at the Department of Algebra, where I was mainly fascinated by studying the dynamics of discrete dynamical systems. And today's talk will be talking about a part of my doctoral thesis. So yeah, I got very fascinated with the phenomena you observe in many dynamical systems that iterating over and over, even some very simple function or rule, can produce this complex behavior, which is very, very hard to predict and sometimes has these fascinating visualizations. So what we see here are just animations of some two-dimensional automata. And what people have looked at widely is that some kind of automata produce interesting behavior, like the one at the bottom, and some not, like the one at the top, where everything converges fast. And so my main two questions of interest for my PhD thesis was how to formally identify systems which look interesting. And the second question is how to measure what can a given system compute, or whether it can even compute something or not. And this talk will be about the second question, mainly because we have, like in the thesis, showed some quite interesting new connections to general algebra and how some of these questions can be answered using the tools of general algebra. So I was told that maybe not everyone's familiar with the concept of cellular automata, so let me briefly go through it. So a cellular automaton, also abbreviated to CA, typically consists of a d-dimensional grid of cells, so just the integers to the power of d. But in this talk, we'll mostly talk about one-dimensional ones. So these are shown on the diagram. And each of the cell has a uniform local neighborhood, which is parameterized with radius r. So what you see in the picture is radius equal to 1, which means every cell has access to itself, its leftmost neighbor, and its rightmost neighbor. Then each cell can be in a state from a finite set of states, usually denoted S. So it can be, for example, the set 0 and 1. And once we assign to each integer position one state, we get something, this ensemble is called a configuration. And the last element of a CA is the local update rule, which in the one-dimensional case is just a function from S to the size of neighborhood, which is just 2r plus 1 to S. So here, in this case of a neighborhood of size 3 and 2 states, the local rule is just a simple ternary Boolean function. And the crucial aspect of the CA is the iterative application of this local rule. So how can we update such a configuration? So at a particular position I, we look at the state of the cell together with the state of its left and right neighbor, and that gives us a configuration of the neighborhood. And we can look into the rule table, what is the output of our local rule there, and this is how we update the cell at position I. And the crucial thing is that we do this update in parallel for all the cells at once, And this produces the configuration at the next time step, t+1. And so this local rule, updated synchronously in parallel to all cells, gives rise to a global dynamics, or a global rule F, which is a mapping from S to the Z to S to the Z. Yeah. And what is crucial for this talk is to notice that with each cellular automaton, we can identify an object, which we call its local algebra. And it is just the simplest general, like the notion, I'm sure you know the notion of a general algebra. So this is just one of the simplest possible algebras in the sense that the state set is finite and there is only one operation F. And this subscript R just denotes what is the type of the algebra. So in this case, the arity of the function F is just 2R plus 1, right? Because there's 2R plus 1 inputs to the function F. So this is an important notion to remember. Yeah, so cellular automata are typically studied in 1 and 2 dimensions, either on an infinite grid, like I just showed, or sometimes for practical purposes. There is some cyclic boundary conditions assumed. So in 1 dimensions, typically this would create this kind of cyclic grid. In 2 dimensions, this would create a torus. And once we have that, we can look at simulations of what certain different rules give when we iterate them. And this produces the so-called space-time diagrams. So in 1 dimension, the first row is just a configuration, initial configuration of the cellular automaton. Typically 0 is represented by 1 and black by 0 is represented by white and black is represented by the state 1. And the time is progressing downwards, so each subsequent row corresponds to 1 iteration of the cellular automaton. And in 2D, usually we show the space-time diagrams as these kind of animations. And so there could be a whole talk about why cellular automata are extremely interesting, but the history of them is fascinating. I would say they became popular after the research of John von Neumann, who was interested in the fascinating questions of whether there could exist machines that produce themselves. And the application was very science fiction. So the idea was that if we ever want to colonize some other planets, it would be expensive to deliver all the machines and all the materials and all the people to build new machines to colonize the world. So it would be the most effective to be able to build machines that can on that planet already reproduce themselves and continue with whatever work they were doing. But at that point, it was not at all clear whether this is possible, because how can it be that a machine with a certain complexity can reproduce itself, a machine with the same kind of complexity? It feels natural that a machine could only build a machine which is kind of simpler than itself. But the environment which proved very fruitful for this result, which is a very formal one, was exactly the environment of cellular automata. And von Neumann basically defined a particular cellular automaton with multiple states. And within that cellular automaton, he defined an initial configuration corresponding to this kind of machine, which is called a universal constructor. And the way it works is that whatever description it gets on its tape of some kind of ensemble of states in the cellular automaton, it is able to interpret what is written on the tape, and based on it, it's going to build that particular description of states. And so then the crucial thing is that it can receive a description of itself, and then it can basically build itself, build the tape, and copy the information from the original tape to the new tape. And this then activates the construction of itself again and again. And what is really mind-blowing about this is that he kind of defined this construction before the structure of DNA was discovered. So before it was discovered that the way that biology reproduces itself is by this double use of information. So first to interpret it to build a new structure, and then to copy it so that the new structure can also build itself. And since then, various kinds of automata have been studied. So here is another kind of self-replicator, but a very simple one, where these kind of loops would multiply. And maybe the fascination really came with the observation that even very compact automata with just very few states, so here you see a one-dimensional automaton with 2 states, or a two-dimensional automaton with 2 states, and very simple update functions can produce behavior that is very complex. And somehow the really formal argument showing that these kind of automata are complex is showing that they can compute very hard tasks. Actually, they can compute any task that is computable. And so those are pretty impressive and elaborate results. And so since the beginning, cellular automata have been tied very deeply with the notion of computation. And so this is what we will focus on today. So a summary of this introduction is cellular automata are good to study because they're one of the simplest models where this kind of complex behavior that is hard to predict can occur. They're fast to simulate and they produce these fascinating visualizations. And we will now focus on the question of, given a cellular automaton, how can we measure what it can compute? And unfortunately, I don't have time to go through all the previous works that tackled this question. So to be very simplistic, if we want to see whether a cellular automaton can compute some kind of task, we need to have inputs to our tasks and somehow encode it into the CA environment, then let it iterate for a bunch of steps. And then we have to somehow decode from its space-time diagram the information about the output. And what is not at all clear is how to choose suitable tasks for the CA environment, which would be challenging enough, and we would be able to find cellular automata which can solve them using this very massively parallel environment. And what is also not clear is what kind of encoding and decoding mappings are allowed. So typically in the literature, people have shown that CAs can really solve various tasks, but it is not really formally defined what are the properties of these encoders and decoders. And it is crucial to have a formal notion of them, especially if we want to show negative results, which are definitely missing in the literature a lot. So it would be super interesting to show that certain kinds of automata cannot compute anything hard, but it is not at all clear how to do it if we don't know what are the allowed encodings and decodings. And so drawing an analogy to the classic theory of computation, where let's say the most powerful computer is the one that can reproduce the results of any other computer. So if you don't know Turing machine, don't worry. You can, for example, imagine that you're comparing your laptop to a calculator, and clearly your laptop is computationally more powerful because whatever problem your calculator can solve, your computer can solve as well. So then naturally, let's say the most powerful computer would be the one that can really reproduce the results of any other computer. And drawing this analogy to cellular automata, it seems quite natural to compare cellular automata between each other. So the goal would be to define some kind of notion of a relation between cellular automata based on whether one cellular automaton can simulate the dynamics of another one. So here, just very vaguely, this automaton above seems to be somehow copying the dynamics of the automaton here. So we could say it's computationally stronger or equal to the bottom automaton. But so, yeah, informally, we could say that a CA is simulated by B if each spacetime diagram of A can be, after some suitable transformation, effectively reproduced by B. So effectively is important, because if we allow this transformation to be any kind of mapping, even some uncomputable one, then it would not really guarantee that it is B which is doing the computation and not just the encoding itself. But now the crucial aspect is like, what is a suitable set of transformations? And maybe now is the time to give some very simple examples. So maybe some of you are familiar with the equivalence classes of elementary cellular automata, which are just these 1D automata with 2 states and radius 1. And so here you have the rule table of one particular such automaton, and here a specific space-time diagram. And for example, one transformation can be just reflecting the space-time diagram along the y-axis going through the cell at position 0. And it turns out that there is another automaton which exactly produces space-time diagrams, which are this reflection. So it seems quite clear at this point to say that, okay, somehow this CA can reproduce whatever this CA does, and vice versa, just because we can use the simple transformation of reflecting the grid. And I would classify this kind of transformation as a geometric one, because somehow we're transforming the geometry of this grid space, right? And let's contrast this with a second example. So again, we have our one fixed cellular automaton. Another transformation we will use is of a different kind. So now the transformation maps every state 0 to a state 1 and every state 1 to a state 0. And it does this for all the cells, cell by cell. And this produces this dual, or let's say reversed cellular automaton, which now where the role of the state 0 and 1 is exchanged, right? And so in this case, I would dare say this transformation can be classified as an algebraic one, because what we are doing really is modifying the local rule of the CA and not the space, not the geometrical space of the grid. And indeed, this kind of transformation is reflected by a transformation of the CA local algebras, and clearly by the fact that there is an isomorphism between A and B, exactly witnessed by the mapping that switches the role of 0 and 1, right? So what we will be talking about today is just the algebraic transformations. I wouldn't, yeah. So geometric ones is, I would say, future work, or even a different line of research, because not necessarily the tools used today could be applied for that. But in the time that we have left, my goal is to introduce 4 canonical operators: the operator S, H, P, fin, P finite, and C, which I will try to persuade you why they are very natural to consider. And I think they're so far basically, those are the suitable transformations whose compositions will give us all the algebraic transformations that have ever been considered in the literature. So that this gives a very generic or general definition, which we will work with. Yeah, so let's maybe delve into what these operators really are. Are there any questions so far?
Te la pregunto en español, Aloncito.
Ok.
Para no. O sea,
Sí.
La pregunta que me surgió ahorita, o sea, ya ves que en la regla 110 y 137 o algo así, no me la sé de memoria, dice como que tiene el espacio y el dual, ¿no? Y como que hay un isomorfismo. Entonces, el cambiar de uno a otro te da mejor, digamos, tú que nos hablas de la topología, ¿te da más propiedades cambiar de un espacio a otro, o para qué lo hacen? Fue lo de diario.
She mentions about the previous slide, I think, in the previous slide, that yes, that you changed, right? You are changing basically exchanging zeros and one. So she asks if, in this case, this cellular automaton, one would be better than other one, or it means that they are equivalent, basically?
So, right. In this case, the automata are equivalent because the transformation is a bijection, right? So B can reproduce any dynamics of A via this transformation, and this transformation is even is inverse to itself. So that also means that using the same transformation, A is able to reproduce any dynamics of B. So intuitively, in this computational sense, these two automata should be somehow computationally equivalent. And it is reflected in the fact that it is very easy to see that the local algebras of these two automata are isomorphic.
Okay, thank you.
Okay, thank you. Sí.
Right, but sometimes it can be that B can reproduce any dynamics of A, and at the same time we can show that A cannot reproduce dynamics of B, and then it would mean that B is really computationally stronger than A. But this example is extremely simple, but I thought it's something you might be familiar with, so it's good to start with this. Good. So, okay, let's go for the operators. So the first natural operator to consider is based on the notion of subautomata. So from now on, let us consider two local algebras of CAs. One is denoted by A, the other one by B, and it is very important that they have the same radius, because that implies that these two algebras have the same type, or in other words, that the functions have the same arity. So we can naturally consider homomorphisms between the algebras, right? And so let's start with the CA point of view, and then we'll go to algebra. So let's say we have these two CAs. A has global rule F, has these two states, black and white. And this is an example of a space-time diagram of A. And we say that A would be a subautomaton of B. In this case, this B has 4 states. If there exists an injective mapping E, which maps the states of S into the states of T. So in this example, for example, white is mapped to yellow, black is mapped to blue, such that whenever, or for any initial configuration of A, we can map it via this encoding bit by bit. And it does not matter if we first encode and then apply the global rule of B, or whether we first apply the global rule of A and then encode. This diagram should be a commuting diagram. And already this commuting for one step, it's easy to see that it's going to commute in any time step. So really what we have is that each space-time diagram of A can be embedded into a space-time diagram of B. And notice that in B, we don't really know what's happening to the states red and green. They can really produce any kind of behavior, but on the subset of these two states, we are guaranteed that B behaves like A. And in such a case, we would say that A is a subautomaton of B. And what this corresponds to algebraically is that the local algebras are in the following relation. Basically, A is isomorphic to a subalgebra of B. And we can also write it that A is an element of S of B. So this operator S, what it's doing is that it's looking at all the subalgebras of B up to an isomorphism. Is this more or less clear? Okay.
Yes, thank you.
Perfect. So we can continue with the second natural operator, which is the quotient automata. So again, if we have two automata, we say that A is a quotient automaton of B if there exists a surjective mapping, we can call it pi, that maps all the states of B onto the states of A. For example, it can map them like this, such that whatever initial configuration we start with for B, it does not matter if we first map the states onto the states of A and then apply the global rule of A, or whether we first apply global rule of B and then map and project the states of B onto A. Again, this diagram should be commuting, and it is easy to see that it actually has to commute for an arbitrary number of iterations of the global rules. So it is, again, this gives us that whatever spacetime diagram of B we start with, if we somehow forget some arbitrary information by projecting the state space to a smaller one, we obtain all the possible spacetime diagrams of A. And again, you see that this translation mapping is a very simple mapping, which is very local. So obviously it is, it is effective. And again, this corresponds to a natural relationship between the local algebras. So in this case, if such a mapping exists, it is the case that A is isomorphic to a quotient algebra of B. And in this case, we would say A is an element of H of B. So here H stands for homomorphic images. So basically the operator H, what it does is that if it has some algebra B, it's going to produce all the quotients of B up to isomorphism. So having these two operators, it seems natural to combine them. So given some automaton B and having its local algebra, we can look at the quotients of B and subautomata of the quotients and quotients of the subautomata of the quotients. And we will get potentially more and more automata that B can kind of simulate. But what is so far boring about these two operators is that they reduce the number of states, right? And by definition, each cellular automaton has a finite number of states. So obviously, if we only consider these two transformations, every automaton would only be able to simulate a finite number of automata. So it is natural to be able to also blow up SCA in size, and this is where the next two operators are coming in play. So a very natural one is considering a product of two automata, which is done in the most straightforward way. So if we have two local algebras of CAs, we can consider the product to consist of the product of the states and the product of the functions. So now you can visualize if A had dynamics like this and B had dynamics like this, then A times B would have an initial configuration consisting of both the initial configuration of A and B, and for the part that corresponds to A, the global rule F is applied, and for the part corresponding to B, the global rule G is applied. So this is one way how we can increase, let's say if we have two automata, then we can kind of say that they simulate their product in a way, which also feels natural. And this brings us to the operator P finite. So P stands for products, and naturally we can only consider finite products because we have to ensure that the product CA we obtain still has a finite number of states, because we define cellular automata to be objects with finite number of states. And yeah, so more generally, P finite can really be an arbitrary product of finitely many local algebras. Here I just showed two because one can then iteratively define larger products. So far so good. These three operators seem to be very natural ways to look at the relationships between local algebras. But the crucial component we're missing so far is somehow the iterative application of the CA local rule. Because all we have done is compared these very simple objects corresponding to, let's say, one iteration of the CAs. But the complexity of cellular automata comes from iterating them as many times as we need. So this brings us to the last operator, called the iterative powers, which answers to the following question. If we have an automaton B with this kind of local algebra and global rule G, then naturally we can iterate G to obtain whatever powers G to the n, because it operates on the same set, right? But so the question is how to create a local algebra corresponding to this iterated global rule. So the theory tells us that there exists a cellular automaton whose global rule will be G to the n. But so what kind of local algebra will this CA correspond to is the question. So let's take a very simple case of a ternary Boolean function G. So the first natural guess, if we want to, for example, construct a local algebra corresponding to the fourth power, so G to the 4, would be to just take more cells than the original 3, and notice that in each time step, the local rule somehow reduces the size of this finite configuration by 2. So if we had 2 times 4 plus 1 states, after 4 iterations, we would end up exactly with 1 state. So the first natural guess for the local rule of this iterated automaton would be exactly this one. We look at a larger neighborhood and we iterate 4 times to get just 1 state. But the technical problem with this kind of iteration is that now the algebra corresponding to the fourth power will not have the same type as the original algebra because the neighborhood size increased, right? So there is a trick known in the literature for a while, which is called grouping or bulking. And that's that instead we will enrich the state space of the CA and group together a bunch of cells that are consecutive. So we're kind of partitioning the CA grid into larger supercells. So in this case, with the fourth iteration, we will be grouping together 4 states. And one can easily check that if we start with like 3 supercells of size 4, after 4 iterations, we will end up with exactly 4 states. So we can now define this local rule G to the 4 to be exactly this local rule, which is again a ternary function. So we're preserving the type, but we're enriching the state space. And doing this for larger and larger iterations gives us a whole sequence of algebras, all of the same type, but having larger and larger state space. So the original CA, if it had states T, then the local algebra corresponding to the second iteration of the CA would have T to the square states, and so on. And this brings us to, this is another showcase of iterated power 3. So this brings us to the last operator Xi. This is because it looks kind of like a box, and we are kind of grouping together into boxes of cells. So Xi of B is exactly all the iterated powers of B. So each B to the n belongs to this operator.
So, sorry, but one question there. T square is the Cartesian product of T with itself, right?
Yes.
Okay.
Yes. So you can see, for example, for the third power, the supercells is the Cartesian product of T with itself 3 times, right? Because we have 3 original cells, or here we had 4. Yeah.
Okay,
yes. So we started with some natural algebraic operators, and we added one that is algebraically quite non-standard one, but it is crucial for the study of cellular automata because it helps us to talk about an arbitrary CA iteration. right? Which is this operator C. And now we can proceed by defining what is the suitable set of transformations. And this is the definition. So we say that A, being a local algebra of some CA, is simulated by B if A can be obtained from B using the operators H, S, P, fin, and C. So what we can do is consider any iterated power of B. We can consider finitely many of such iterated powers. We can take their products. We can look into the subalgebra of that crazy product. We can look into quotient of that subalgebra. We can again take whatever products of such objects and so on. And this gives us a relation between A and B. And what is quite nice is that actually it only suffices to take the 4 operators exactly in this order, and it's already generating all the possible combinations. So, as I was just explaining, maybe you have to take substructures and then quotients and then more substructures and then quotients, but it turns out you don't need to do this ad infinitum. In fact, you just need to apply each operator once, and it already gives you a set that is closed under all these 4 operators. And the order is very important. So first, one has to look at all the iterated powers of B. Then we do finite products of those powers. We get this finite object. Then we look at subalgebras of that. And in the end, we look at quotients. And this is already enough, and it's something I proved in the thesis. But actually, it's not so mysterious. If we look at this general algebra intermezzo, so these are some very basic notions from the field of universal algebra. And I think this is also a nice motivation for why exactly these operators might be the interesting ones to study. And so suppose we have a K, which is an arbitrary class of algebras, which all have the same type. So it makes sense to study homomorphisms between algebras in this class. And suppose we consider the operators H, S, and P. So H and S we already saw. And the only difference between P and P fin is that the general P allows to really take arbitrary products, not only finite ones. And so one result is that the class of algebras is closed under these operators if and only if it is closed exactly in this particular order. So this already implies that whatever class you start with and you apply the operators exactly in this way, you end up with a potentially larger class of algebras, right? Because now it contains all their products, all the subalgebras of the products, and all quotients of the subalgebras of the products. But the point is that applying the operators H or S or P again is not going to increase this set anymore. So now this result is a very natural consequence of this basic result from universal algebra. And if we have such a class of algebras K, which is closed under these operators, it turns out to be a very nice object algebraically, and we call it a variety. And the elementary result of universal algebra by Birkhoff is that each such variety can be axiomatizable by a set of equalities. So once you have a variety, you can describe it in terms of what kind of equalities do the elements of this huge class satisfy. So to have one simple example is we can start with Z, the abelian group of integers, and we can look at H as P of Z. And it is easy to see that this already generates all abelian groups, and thus this kind of variety is axiomatized just by the axioms of abelian groups. So one such identity is, for example, that any 2 elements xy of any algebra in this class satisfies that xy is the same as yx. So that's the commutativity, right? Another one would be associativity. So you can list all the axioms of abelian groups, and you will see that exactly all algebras satisfying it are exactly those algebras that are in HSP of Z. So what we would hope for is that our object, which is HSP fin xi of some automaton B, would also be nice, and we could also describe it in some nice way. The troubling part is the P finite. So allowing only finite products makes for a more complicated object than a variety, and it is called a pseudo-variety, which are harder to study. They can still be axiomatized by identities, but now it's infinite sequences of identities. So it shows it's a harder object, but I nevertheless think that finding such identities for cellular automata would be really eye-opening, as in what is it that they can compute and what kind of symmetries they have. But so going back to our case with this particular relation, what we can now do is we can, whenever we have an A which is simulated by B, we can draw it by this diagram that B is somehow above A. And whatever favorite family of automata you choose, you can start studying what is the structure with respect to this relation. So for each family of CAs, which contains a CA with just one state, it is quite clear that this will be at the bottom because anything can be projected onto a one-element algebra. But an interesting question is like, would there be a universal CA for this class? Which means, is there a cellular automaton that could simulate all the other automata? And these questions are in general quite hard, but what we can start with is simpler questions, and that is kind of progressing from the bottom up. So we can, for example, say that CAs that lie just one arrow away from this minimum in this hierarchy are level 1, which means they're still quite simple. They can only simulate potentially themselves and the C and the one state CA. And so this gives us some computational metric of complexity, kind of counting how far away from the bottom are CAs in this hierarchy. And this brings us to one of the main results of this part of my thesis, which showed that if we look at affine cellular automata, they lie exactly at this level 1 distance from the bottom element, meaning that if a CA is linear or affine or abelian or has some notion of a plus with respect to which it is linear or homomorphic, then it is limited in terms of what it can simulate, which is not surprising, but still quite technical to prove. So super formally and very fast, if we have a CA with this local algebra, we say that it is affine over some finite field Fp, if V is a finite dimensional vector space over Fp, and the local rule is an affine mapping of vector spaces. And the result is that if we have B, a cellular automaton which is affine over a finite field Fp, and B satisfies certain mild conditions, which can roughly be said that the outer components of the local rule have to be bijective, then all CA simulated by B are also affine over Fp, and they satisfy the same condition. So if we fix a finite field Fp and consider a class of all affine automata over that finite field, then we know that they can potentially only simulate other cellular automata from this class. So they have to lie at the level 1. It is not so trivial because there's examples of CAs which don't satisfy this condition, and then they can simulate some non-affine ones. But on the other hand, this is just an example, and the theory is quite more general. In fact, whenever the CA satisfies this kind of equality, it can be seen as some kind of symmetry of the CA that limits what the CA can compute. And so the crucial thing to show is that this kind of symmetry is preserved under all the operators, that it is preserved by iterated powers, by the finite products, by the subautomata and the quotient automata operators. And so the CA need not be affine, it can also be abelian, meaning that this state space has a structure of some abelian group, and this similar limitation would hold. And to quickly finish, so this gives a pretty nice negative result, which is quite general. So it talks about large classes of CAs and saying that they can never be universal, for example, with respect to this particular relation. But a positive one is also that we looked at all cellular automata. Now their state space need not be, like, cannot be an arbitrary vector space, but just the finite field itself, and the radius has to be 1. And for such CAs, we have given a complete characterizations of all the automata that can simulate. And this result is not yet really published, and maybe it would be nice to talk about it at the next automata conference. And that's the end of the talk. Thank you for your attention.
Thank you very much. Thank you. Well, are there any questions here also, in case someone has? I have a couple in the meantime. Well, maybe. I wanted in these slides, you in this one you mentioned the outer components of its local rule are bijective. Does that mean that they be permutative, or what they call be permute? Is that definition, right? It is.
Exactly. Yes.
Okay, great. And another question, or maybe I don't know if you, because part of the problem that you mentioned with this operation is that you consider only finite products, and you want to consider only finite products because you define cellular automata as not only over finite alphabets, right? But you know, there are few people that have looked at cellular automata over infinite alphabets as well. So, for example, and there are some things, I mean, there are many things that are preserved. There is even like a Curtis-Hedlund theorem for these cellular automata over infinite alphabets, that you only have to replace the continuous part of the classical theorem, right? That the classical theorem says that a transformation will be a cellular automata if it's continuous and commutes with the action of the group, or shift commuting. And with an infinite alphabet, you have to replace continuous by uniformly continuous. But it still holds. At the end, it doesn't matter for you because you are working with the local rules, so will not make any big change. So I wonder if you allowed your cellular automata to have infinite alphabet, maybe do you think that would make something easier for you, or maybe that automatically the infinite alphabet ones will be the most powerful ones, and that's it? I don't know.
So that's a good point. I think I was dwelling on the finiteness of the alphabet because this question was a priori motivated by somehow the efficiency of the computation and the fact that the encoding and decoding mapping have to be simple enough. But now, if you have a CA with an... So first of all, yeah. It is not so the problem is that if you had a CA with an infinite alphabet, it's not like simulated efficiently. But nevertheless, even I guess omitting this part, then it would be really interesting theoretically to look at this generalization. Well, it would make the situation simpler by the fact that now we would study objects which are varieties, and there is an abundant theory which studies those in universal algebra, and it would be super cool to see what kind of results could be applied to say things about cellular automata. Another thing is that if we want to show negative results, we can make the operator be even more general, so consider infinite products. And if we can show that even in such a case, as a class of CAs is limited in terms of what they can simulate, then it also implies it would be limited with the finite B operator. So when showing negative results, I think it is meaningful to look at this more general product. And the last question, which I didn't think about too much, but it's quite interesting, is to see, let's say you start with a finite CAA, then you look at the infinite products of its iterated powers, and you end up with some crazy CA with infinite states. And then you show that there exists a projection to another finite automaton. So we would still have the relationship between two finite automata A and B, that one can simulate the other one, but with the intermediate of going to some crazy infinite structure. And it's not like I have examples of that, but it would be quite interesting to see what would that mean.
Great. Thank you. Yes, well, very interesting work, very interesting. Is there any other question?
Yo tengo como un comentario.
Sí, adelante.
Ya ves que presentó una ventanita, ¿no? Una serie. Y luego hizo iteraciones y mandó como a un solo como cuadrito, ¿no? Entonces después mandó como eso y luego lo mandó como que a la ventanita local. Y por lo que no hemos visto contigo, como que lo local define pues ya el autómata, ¿no? La propiedad local. Entonces como que eso que nos expuso es precisamente que prefirió la segunda a la primera. ¿Entendí bien?
Perdón, la segunda, la primera de qué?
O sea, ya ves que presentó una donde iba un solo cuadrito, ¿no?
Ah, ya, sí, exacto, sí. So I think Paz is asking about your slide where you iterate, where you define the operation of iteration.
Yes.
So, exactly. So I think de esa te refieres, ¿verdad, Paz? So,
sí, claro.
She asked that basically, if you can explain again why you discarded the first sort of diagram and you had to put the second diagram where you have to do this grouping.
Right. So the idea of these simulations and transformations, or of the previous operators H and S, is that what we're doing is we have two local algebras, and we're basically looking whether there is a homomorphism between them. So either a surjective homomorphic image, or like a surjective homomorphism, or an injective one. And that gave us a relationship between two cellular automata. But in order for this to be well defined, we have to have the two algebras of the same type or signature. So in the same sense as it makes sense to look at homomorphisms between groups, but it does not make sense to look on a homomorphism between a group and a monoid, just because they have different operations. It would not make sense to look at a relationship between a CA whose local rule has arity 9 to a CA which has arity 3. And so it gets a bit technical, because if you have just two cellular automata and they have different sizes of neighborhoods, what you can first do is kind of define that that they will both have the same, and let's say the one, you can redefine the CAs to have somehow larger neighborhoods, which would take into account both cases, and then you can start looking at homomorphisms between them. But the problem is with this sequence, if we consider this kind of naive case, we would really get CAs with larger and larger neighborhoods, and there would be no finite upper bound for the neighborhood. And what we ultimately want is still relate or find homomorphisms between the CAB and its iterated powers. And we wouldn't be able to do this if this sequence had an increasing size of the neighborhood. So that's the trick, by increasing the state space to preserve the neighborhood. This is like a very classical trade-off. If your neighborhood is big enough, you can always hide more cells into a supercell to reduce the neighborhood size, and this is exactly what's happening here.
Yeah, exactly. So you keep the same R, basically the same radius, and in exchange of that, you have to increase the size of the alphabet, right?
Yes, exactly.
Thank you, thank you.
Thank you for the question. I think it's quite confusing to see this iterated powers. Yeah.
Yes. So I think there's a question here as well. Maybe just one last quick question. Pero a ver, he will ask it in Spanish and I will translate now in a moment.
Noté que todo el tiempo estaba hablando de los autómatas celulares en un álgebra.
Ajá.
Y, o sea, usa la regla local como para definir esta álgebra.
Ajá.
Pero entonces hay como una correspondencia entre álgebras y autómatas celulares.
Ajá. So yeah, he asked about your correspondence between cellular automatas and these algebras, right? So he says basically. So maybe you can clarify that again. I mean, as I understood, basically the local rule will be the operation of the algebra, right? So it will
exactly.
be one algebra with just one operation, but this operation has arity r, which is the radius of the
Or well, technically the arity is 2r plus 1.
Sorry,
right?
sorry. Okay, sorry.
Yeah.
Okay, yeah. Okay, the arity is 2r plus 1. Okay. So it has to take 2r plus 1 elements in the alphabet. It operates them via the local rule, and it gives you one element again in the alphabet, right? Because that is the
exactly.
Yeah, I think that's a very clever trick, very clever thing. I wonder. I mean, has somebody done that before, or was it first in your PhD thesis that you consider that?
So the previous work I wish I had time to mention was definitely this paper by Mazoyer and Rappaport, where they already define these iterated powers, and they look at some negative results only for the operator S and for the operator Xi. So looking at just subalgebras of iterated powers, which is in some sense easier. But somehow indirectly, they never really consider global dynamics of CAs. They only work with these local algebras. So for them, a CA is the local algebra.
Mm-hmm.
But in some sense, they never say the word algebra.
Okay.
So I'm sure like I feel like there have been people who have been thinking about cellular automata
in that way.
Using this notion. But the thing is, there is so much theory about general algebra, which I don't think has not been harvested. So I think this connection has not been thought through too much. And I feel like the field of universal algebra might prove quite fruitful to study CAs.
Yeah, I think it looks very nice. Great. Okay, so thank you very much again, Vara, for a very interesting talk. And thank you, everyone. Gracias a todos por asistir. So we'll keep in touch. Thank you very much. I'll send you the link of the video.
Perfect. Thank you so much. Have a nice day.
Thank you. Bye-bye. Thank you very much.
Nos vemos. Gracias.